In this video, we're going to cover two important theorems about integrals, and you should see some relationships to what we've learned with derivatives in the past. So we're going to do MVT, mean value theorem, with integrals, and it's highly related to average value. So our first question here says, do you have an idea what we might mean if I asked you for the average value of this function over the interval from A to B? So sometimes students would say, well, an average that they should pick a number in the middle, either horizontally, or here's our f of A height, and here's our f of B. So another idea might be that we should pick a height exactly in the middle, and neither of those values is exactly what we're looking for. So the average value of a function actually depends more on how fast or how slow it's changing. And one way that we can look at this is if we think about the area under this curve, we have one viewpoint about the shape of the curve by how much area we have below here. And we know that there's some rectangle that has the same base, b minus a, and the same area as this yellow rectangle. So if we shaved off some of this higher area and filled in below, so for example, if I chose, and I don't know if I chose exactly correct, I'm just doing this by observation, but does it appear that this red rectangle might have the same area as the yellow shaded integral? So that's the idea of finding an average height. So this point on the function produces what we're going to call the average value of the function. So what we just came up with was the idea that the average value of a function is taking the integrals area, so that would be a to b of whatever our function is here, f of x dx. So if we took that yellow area and we divided it by the base, dividing by the base is the same as multiplying by the reciprocal, that would give us an average height. So if you think of this rectangle as having the average height of the function, so you have just come up with a theorem to find the average value of a function on an interval. So remember this geometric interpretation. So you're looking for the height of a rectangle that has the same base and the same area. So this is our integral, gives us that area. All right, so here it is written in theorem form, exactly what we just talked about. So let's see if we can put that into work here in some examples. Often they are much easier than it sounds. So in this problem here, we already know that the area is 60, and our interval goes from -7 to 5. So our average value is simply taking the value of the integral and dividing it by the width of the base, so from -7 to 5. So our average height. So you're already given the information. Don't make that problem harder than it is. Let me draw, I'm going to pause and draw an example of a graph here just to make sure we've got the right idea. So here's an example of a shaded area, and of course we don't know what our function is here, so I just drew a random curve, and our interval went from -7 to +5. So the integral is that yellow shaded area. That's where we come up with the 60. And we know the base of the interval is 12. So our average height that we want then for a rectangle, so this green rectangle, would have an area of 60 if our average height is 5. So again, if you have that visual idea, it makes it much easier to remember how to find the average value. So in 2a, we have the same idea. We already know the integral is 300 and our interval from 10 to 24. So our average value here, and here our function's name is not f but v, So our average of function v would be our area, the integral, divided by the width of the base, that would be 10. So we would come up with 30. So here we're using our formula that we just found from that theorem, the average value. You take the integral, and here I want to make this a v of t dt. So we take the area and divide by the base, and that gives us an average height. All right, so now in B, let's see if we can interpret this. If v is velocity measured in miles per hour, then what did we just find about the average value? So remember that the average value is a height. The average value is a height, so it is a y-coordinate. So in a velocity function, in a velocity graph, here we know that our x-axis becomes t, time, in hours, and our velocity is in this case measured in miles per hour. So our average height is a y-coordinate. So our v average that we just came up with in this case would be 30 miles per hour. So this is one more way to find an average velocity. All right, let's do another problem. Find the average value algebraically. We're given a function this time over this interval. So our average value, we're going to, and you don't have to rewrite this each time, but until you get used to this theorem, let's write what it is we're going to compute. So here to find the average value, our interval goes from 5 to 0, so you could just make that a 1/5. And we need to find the area, so we'll do the integral from 0 to 5, 3x squared minus 2 dx. And I might not have given myself enough room here, so I'm going to slide over. So our f average is 1/5. And our antiderivative here, raise the exponent to 3, divide by it, and raise this. This will be a 2x evaluated from 0 to 5. So our fundamental theorem, we're going to evaluate 5 here. So, and you don't need to show this arithmetic. Put 5 in and then put 0 in. So there's our capital F of B minus capital F of A. So we've got 1/5 of 115. So our average value is 23. All right, now we're going to go one step beyond the average value. So that's our average y-coordinate was 23. Now question B says, can we find the x-coordinate where the average height occurs? So let me just scroll up here a minute to where I drew this diagram. So notice in this example, this was just a hypothetical example, but now we're asked what is the value of C? So notice again that the average height might occur more than once. So it has to occur at least once on the closed interval because we have an existence theorem, but it could occur more often. So let's find out. This is a pretty simple question now that we've done part A. We already found out in part A that the average height of that function was 23. So this question is saying, where is f of c equal to f average? So we've already found f average. So our function with evaluated at c would be 3c squared minus 2. We want to know when does that reach a height of 23. So we would have 3c is 25, and c would be plus or minus the square root of 25 over the square root of 3. And now notice our interval in this problem was from 0 to 5. So only c equals positive 5 over radical 3 is in the interval we're interested in here. So the value of c is where does the average height occur? And now that gives us the second part here of our topic. That's considered the mean value theorem for definite integrals. So this is really just a fancy way of saying f average. So the mean value theorem for integrals says, where does the average height occur? So if you've already found the average value, then you simply have to say, where does that become the x or the y coordinate? Sorry, let me pause and plug in my computer. So let's see if we can now do the average value theorem and the mean value theorem. They are very closely related. So in question 4, we're simply asked to find the average value. So the average value is simply the area, that's the integral, divided by the base, that's our b minus a. So here we want to find our average value, our interval from 2 to negative 2, and our function is our integrand. So here we'll have 1/4, and I guess I could evaluate that right away. Our antiderivative would be x cubed minus 3x, evaluated from negative 2 to positive 2. And I'll continue up here. So we're finding our average value, 1/4. And now I evaluate our antiderivative at 2 would be an 8 minus a 6. And our function, our antiderivative at negative 2 would be a negative 8 plus 6. So let me be careful about signs here. We've got a positive 2 and then plus another 2. So it looks like we have 1/4 of 4. So our average height of our function is 1. That's the y coordinate. So that's the average height of our function on this interval from negative 2 to 2. Now question B asks, or the second question here asks us now for the same function to find the value where the average height occurs. So mean value theorem, remember mean is average, so the mean value theorem for integrals is simply saying when or where, let's try spelling that right, where is f of c equal to f average. So our function evaluated at c, where is it equal to 1? So we've already done if we've already found the average height, then we've done the hard work here. So c is equal to plus or minus 2 over the square root of 3. Both answers are in our interval, so we'll keep both of those values. So MVT is an existence theorem. It is saying where is the value of the function equal to the average height. And if our function is integrable, then we know that there will be an average height. So where does it occur is the value of c. All right, so let's try again. Here we have a sine function from 0 to pi. So you could, right away, we're finding the value of c. So remember that another name for this would be our f average. So when is f of c equal to the area divided by the base? So our integral has an integrand of sine of x. All right, so we want to do some work here, and you could work on both sides. So this is going to become sine of c. And on this side, we want pi minus 0, so of course you could just put 1 over pi. So our integral, so sine is the derivative, so we have 1 over pi. Sine is the derivative not of cosine, but of negative cosine, so that the two negatives would cancel out. So our fundamental theorem here, we have our f of c side on the left. Let me copy that. We have sine of c on the left side of that equation. And now if we evaluate, the opposite of the cosine of pi would be the opposite of negative 1, so that would be positive 1. And the opposite of the cosine of 0 would be a negative 1. So we now have sine of c equal to 2 over pi. So we could write our answer here as an inverse sine. So c is equal to arc sine or inverse sine of 2 over pi. That would be an acceptable answer. Or you could grab your calculator. I think I've already done that somewhere. Let me grab a calculator and find that. 0.6901 radians, if I'm reading my calculator correctly. So either one of those answers would be acceptable. Question 7. Describe 2 ways now that we could find average velocity. Well, we've been doing this since first semester. So over the interval from 0 to 3 hours, we could say that the average rate of change is the slope of a secant. So position 3 minus position at time 0 over 3 minus 0. So this is the slope of the secant of the position function. So we've known that for quite some time, that that's one way to find average value, average velocity, that is. If we're given the velocity curve, now we have a second option. The average velocity over the time period from 0 to 3 could be our area, our integral, divided by the base. B minus a would be 3. So this is the average value function, average value theorem, I should say, of the velocity function. All right, and now hopefully this becomes the aha moment. So let's take a look at this. What would be the antiderivative? If we evaluated the integral, what is the antiderivative of velocity? And hopefully you say, oh, look at it, it's exactly the same thing. The antiderivative of velocity is position. And then we evaluate from 0 to 3. So lo and behold, do you see that we are doing exactly the same thing? So the slope of the secant of the position function and the average height of the velocity function are indeed equivalent. All right, so now we have to make sure we can understand the units and what we're coming up with when we evaluate some of these. So if you are integrating velocity from 0 to 5, we know that that gives us the displacement or net distance. Displacement or net distance. And I hope you'll use the term displacement. Over the time period from 0 to 5 seconds. Over 0 to 5 seconds. And I actually should say displacement in feet. So when you're asked to interpret, you're always being asked whether you can come up with the terminology and the correct units. What's the difference in letter B? The difference in letter B is we're integrating the absolute value of velocity. So we would be making all of the velocity positive. So if you were going forward, backward, once you do the absolute value, then you're finding the total distance. That would be the total distance in feet over 0 to 5 seconds. So you get a very different answer when you put that absolute value. All right, so what about integrating acceleration? If you integrate velocity, you get the displacement. If you integrate acceleration, that our term there for the change in velocity. So displacement is the change in position. So if you integrate acceleration, this would give you the net change, I should say would be better. The net change in velocity in feet per second over the time period from 0 to 5 seconds. All right, and I'm going to save time here on the video, I'm going to switch here where I have these already written, and you can pause the video if you need to get more of this. So in D, notice we've seen this just a minute ago. This is the slope of a secant on our position function, gives us average velocity. So what happens if we do the slope of a secant on velocity? That would give us average acceleration. So you have to make sure that you're labeling these in the correct units. And here I wrote feet per second per second. Could you write that as feet per second squared? Yes, that would be fine. And if we look at F, G, and H, do you notice that it looks like the average value of the functions that we were just talking about? So when you take an integral, that's an area, divide it by the base, and you're getting an average height. So if you are doing the average value of position, we would call that average position. So it's an average height of this function itself. So this is in F an average position, in G it's an average velocity, and in H it's an average acceleration. So just be very careful that you label each of those with correct units.